Alright, so we got 23 questions. There's your typical freebie at the end. So that means, you know, each one is worth a little more than 2 points in the whole 50 points. And then just the way you grade these, those two exams 4A and 4B just get added together as a single exam, those scores. The topics include states of matter. You'll have a couple questions on that. That would be liquids, solids, liquids, gases, and then also plasmas. There's nothing about dark matter, so you can just sort of bypass that. But yeah, remember what a plasma is, right? That's an ionized gas. That's usually a hot gas, although it doesn't have to be a hot gas. Like those little balls that you see in those, I don't know, those novelty stores where you put your finger on it. That's a plasma. Density. Need to know how to calculate density. Pressure measurements. You know, that's like with a manometer where you have something like this, or something where you have like a little container over on the side, and then also a barometer. Make sure that you know how to calculate the pressure for those. Be careful with your units on those. We'll go over those in just a bit. Pressure measurements, Archimedes Principle. Something that's on the test that's not commonly on other exams is the concept of apparent mass or apparent weight. Those of you that are in lab have done this, but let me just do a quick primer on it. If I have an object that, say, has a mass of, I don't know, 12 kilograms. This object, mass of 12 kilograms, that's, you know, a measure of the matter that's in that object. But then, if I put that object inside of a container that's filled with liquid, and then I say it appears to have a mass of, I don't know, 5 kilograms. The object hasn't actually lost mass. What's happened is that I have a buoyant force that's pushing up on it. So the buoyant force is pushing up, which causes it to appear to be less massive than it is. So do you know what the buoyant force is for this object? If it really has a mass of 12 kilograms, but now it appears to have a mass of 5 kilograms, what would the buoyant force be? No. 70, yeah. So I've lost 7 kilograms, right? Because this thing is pulling up with it 70 newtons. And the way that you get that is you say 12 minus 5 is 7. And then to convert that into a force, I would say m times g, or 7 times 10. So that's equal to 70 newtons. Okay? We haven't really done that. We did that in lab, but we haven't really done that in class very much, but you will see that tomorrow. And really the key here is figuring out what is the buoyant force. I might not ask you what the buoyant force is, but then there are other things that I could ask, like, you know, what is the density of the fluid, or what is the volume of the object, any number of things that I could ask in that have to do with Archimedes' principle. Okay? It's stress and strain. Of course, you'll have an equation, like you'll have to use this equation, F over A equals Y delta L over L. A couple things about this that I want you to be aware of. What is this F over A called? Which is that? That's our stress. And then this is our strain. All right, make sure that you know what those two things are, just how to identify them. That might be important for tomorrow. And then this right here, this is our modulus, our Young's modulus. All right, that's in your equation sheet for different types of materials. And then also, let's say I don't know, hypothetically, asked you a question where I said an object increases in length by, I don't know, 20%. Like, I don't give you delta L, or I don't give you L. I just say that you have an increase of 20% for this object's length. And I ask you, what is the force, or what is the stress, or what causes that increase of 20%? And so the question I have is, what then, if I don't give you L and I don't give you delta L, but I just say that I increase by 20%, what then would delta L over L be equal to? So, the way I want to think about this is, I want to know what delta L over L is. Well, I know that delta L, the amount that it increased, is equal to 20% of L. That is, delta L is equal to 0.2, right? Y'all remember 5th grade? The means a times, right? These keywords. So 0.2 times L. So here, this would be 0.2 times L divided by L. So you don't have to know what delta L are, because I can just take that percentage. You understand what I'm saying there? That you can work this problem if I just tell you the percentage by which it's increased. Because you don't really need to know what delta L and L are if I tell you that it's increased 20% in length. Okay? That's a little bit different than problems I've asked before. It's still the same problem, it's just presented a little bit differently. Okay? You'll see it tomorrow, so make sure that you're aware. Y'all would know what to do if you saw this now? Yeah. Or whatever. 30% would be 0.3, 5% would be 0.05. It's just the percentage. Because of this, that delta L, if it increases by 20%, then delta L is 20% of L. That means delta L is equal to 0.2 times L. So I put that over here, 0.2 times L divided by L. The L's cancel, just leave me with 0.2. Alright? Okay. So those are the two things I wanted to tell you about, the apparent mass and the percentage, sort of showing how to do this stress over strain. And then also make sure that you know these words and what they're associated with. Okay, so Archimedes, stress and strain, pressure measurements, fluid flow, and that includes Bernoulli's and equation of continuity. I have a string of about 4 questions that are one after the other. Mostly they're unrelated. So if you miss one question on one, you won't affect the next one. But there are 2 questions that are related. The first one, where you have to use the equation of continuity to find the velocity, and then the second one, where you have to use Bernoulli's to find the pressure. So, when you're using Bernoulli's principle to find the pressure, that's P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared, you need the velocity in the second pipe. So if I give you a pipe that looks like this, for example, I would first ask you, what is this velocity? And then I would ask you, what is the pressure? So those are 2 questions, but I just caution you that if you get the velocity wrong, then you're going to get the pressure wrong. And I'd much rather you miss 1 question than 2 questions. I really want you to get them both right, but just be aware. Make sure you're really certain about that equation of continuity question. It's not tricky, it's just like what we've been working, but just make sure that you get it right. In fact, while you're at it, just get them all right, and then we'll all be happier. Everybody will be happy, I'll be happy, you'll be happy, right? Okay, fluid flow. Did I miss anything? I think that's it. Yeah, that's it. Let's look at some of the old tests, but first are your particular questions that you have. Yeah, go ahead.
The second to last quick test, I was confused because I thought that if the level of liquid was lower, then I had the most pressure. But that one is the opposite. Is it because it's like a vacuum?
Can I see? This one right here?
Is it like a vacuum?
pressure is greatest right here. You want to know why that is? Okay, let me address that. And if I don't answer your question, if it's unclear, then just let me know. So second class quick test. And you have a situation in that where you have a pipe. Actually, you couldn't see the bottom of that pipe, but then you had 3 standpipes. 3 standpipes, and you know your fluid is flowing through here, and depending on the pressure of where that fluid is, it'll be at different levels. So right here, it was all the way up, here was like halfway, and here it was right there. So it was A, B, C. You are right in saying that there is a pressure pushing down on each of these. It's not a vacuum. These are open. So, you know, if they got to be a really high pressure, they would just overflow. But the pressure in those standpipes is going to be proportional to the height. And so the pressure proportional to the height, that means that it's going to be highest there. Like the pressure will be biggest there. It's always proportional to the height. If your height is bigger, that means that your pressure is going to be bigger. Does that answer your question?
That makes sense to me. I was just confused, like, with the other ones where, you know, where P naught is greater than P, and the level, if it was lower, the pressure was higher.
Well, here, P is bigger than P naught. It has, like, if this is P naught, and if this is P, P is bigger by P naught. In fact, if I were to calculate P, it would equal to P naught plus rho times G times H. Because I have the atmospheric pressure pushing down, and then I have this additional pressure due to the weight of that liquid. I hear what you're saying, but in this case, P is bigger than P naught. But you don't really need to know, well, you sort of need to know that, but it doesn't really come into this problem so much. But the important part of that problem is that the pressure is proportional to the height. Okay? All right, good. What else?
Problem where you have to know if it's P naught minus rho gauge or P naught plus.
Okay. Yeah. Well, that'll definitely come up tomorrow. So I'll ask you a conceptual question and then also a calculation question for that. So let's say that I have, I'll draw it like this because it's probably going to look like this. It's like a monster. So let's say that this is P and this is P naught right here. Say that my fluid levels are relatively like this. That means that I have a height of that column right there. And so the first question is just which is bigger. You know one's bigger than the other. And the one that's bigger is always going to be the one that's on the lower level. So here, P is less than P naught. And so if I know this height, let's say that this height is, I don't know, 2 centimeters, then I would say that P is equal to P naught. If it's atmospheric, that would be 1 times 10 to the 5th pascals. And since it's less, is it positive or plus or minus? It's going to be minus, right? Because P, it has to be less than 1 atmosphere, right? Because of those relative levels of the fluid. Let's say that it's mercury, that would be rho GH, 13,600, 10. And then be careful that you always convert your units, 0.02 centimeters, and then that would be whatever it is. Okay? It's all based on the height, right? It's always based on the height. And these are a little bit different because you have to figure out, is this plus or is it minus? And if P is less than P naught, then it has to be minus, because you know that this value has to be smaller than this value. So that means you have to have that negative right there to take away from the atmospheric pressure, to make P less than P naught. Okay? Make sure that you're converting your units there. By the way, that's true too for the stress-strain problem. I'm going to give it to you in centimeters. I'm going to give you probably the diameter, so make sure you're converting it and you're changing your diameter to a radius. I'm pretty sure that's true. I'm almost confident. I'm pretty sure that I gave you diameter, not radius. But we talked about it in class, I think. So, in one of the gazillion classes that we had on this stuff. All right. Other particular questions? Let's look at some of the old exams. We'll go back a ways. Let's go all the way, follow it. Huh? I think there are fluid problems on this. Exam 3, follow 8. Okay, yeah. Okay, you're going to see some Archimedes Principle problems with buoyant force. Number 15 is a good example of that. So let's take a look. We've done some of these in class. So let's just take a look. A boat has a volume of 3.2 cubic meters. If the boat has a mass of 500 kilograms, what is the total mass of the cargo that the boat can carry without sinking? So I have my boat. It's going to be completely submerged. So the water is going to come right up to the level because I want to know what is the maximum mass that it can carry. So I know that the buoyant force has to equal to the weight of that boat plus its cargo. I want to figure out what is that buoyant force. That would be rho times V times G. It's going to be 1,000 kilograms per cubic meter. It's the density of water. That's on your equation sheet, but you know, just know it. Times V, which is 3.2 cubic meters, times 10. That's 32,000 newtons. So I have 32,000 newtons. The boat itself requires 5,000 newtons. So the total weight of the cargo is going to be 32,000 minus 5,000. Just subtracting out the weight of the boat. Make sure that you read this carefully. This is asking for the total mass of the cargo. In other questions, I've asked for the cargo plus the boat. Just read that carefully if you have a question like this. So that's what, 27,000 newtons, but it's asking for the mass. I don't have 27,000 here anyway, so it's going to be 2,700 be the right answer for the total mass of cargo that the boat can carry. Okay? Get that as right, please. If I can clear this. You're going to have one of these. These are pretty easy, in that if you just recognize that whatever amount I'm increasing my area is the amount that I increase my force. So here I'm going from 0.01 to 1. That's a factor of times 100. Right? 1/100th to 1. I have to multiply that times 100. And so that means my force is 100 times what it was, or 100 times 100. Add 2 decimal places, that's 10,000 newtons. Yeah, 10,000. So, but if you're unclear about that, just say F1 over A1 equals F2 over A2. That's going to be, is this 100 over here? Yeah, 100 divided by 0.01 equals F2 over A2. You'll have 1 or 2 questions about that. Well, you have 1 question where you have to calculate it. Other questions about the principle. What is this principle for hydraulic lifts? This is Pascal's principle, so make sure that you're familiar with those 4 or 5 ideas that we had. Not just being able to describe them, but know where they apply and like know which laws are behind them. Let's just go through those. So Pascal's principle says that the pressure is the same it's only for incompressible fluids. And incompressible fluids include liquids only. So a gas is compressible. You can compress a gas, but liquids and solids are incompressible. So this is true for liquids. Solids are also incompressible, but just practically, you can't use a solid to do this because you don't feel pressure in the same way. That's Pascal's principle. Archimedes' principle says that the buoyant force is equal to the weight of the displaced fluid. I think that's all there is on that, really. That's for Archimedes' principle. The other things that we had were Bernoulli's principle. Bernoulli's principle was based on the conservation of energy. And one implication of it, like the primary implication, is that if the velocity goes up, the pressure goes down. And then the equation of continuity says that it's based on the conservation of matter. And it's A1V1 equals A2V2. Is that all? I think that's all. You have the stress strain. We don't really have a formula or a name for that, but that the stress, that's F over A, it's proportional to the strain. All right, make sure you know all those principles, you can identify them, and you know where they apply. All right, can y'all see okay with the lights? Yeah? Let me clear this. So you know how to do this. In this case, my P and P naught were flipped. We're not really used to it, but here, let's just call this P naught. We'll call this P. So this is equal to 0.2 atmospheres, and I want to know what is height. So I know that P is equal to rho GH. That's because P naught is 0 in this case. So if I want to know the height, so it's filled with water. You might know that already. If it's filled with water, what's the height at, oh, never mind, no. Never mind, I forgot what I said. The pressure is 0.2 times 10 to the 5th, equal to 1,000 times 10 times the height. Now if I solve that for the height, you know what, 2 meters? Right, 2 meters. I know that actually because at 1 atmosphere, the height of a column of water is 10 meters. We did that problem. That's sort of that was the original barometer. And so since it's just 0.2 atmospheres, 2/10 of that would be 2 meters. But you might not remember that. That's fine. Okay? So you can do those. And then we stop there. So let's go back and look at some of these. I think we got many of these. Here, if you squeeze the end of a garden hose, what happens to the pressure? I know if I squeeze the end of the garden hose, I decrease the area. That makes the velocity go up. So what happens to the pressure? Right, the pressure goes down. Make sure you can do those where you're applying Bernoulli's and the equation of continuity. And we did that one. Here, can you find the pressure 9 meters below the surface? Don't forget that you have a pressure right here. So if I wanted to find P, it would be equal to P naught plus rho GH. That is P naught, which is 1 times 10 to the 5th, plus 1,000 times 10 times 9, and so that's 90,000, 190,000 pascals, which is 1.9 atmospheres. Any divers? You know, any dive? You don't dive. You might dive. No. In order to increase by an atmosphere, when you go below the surface of the water, that's just sort of a rough number, is about 30 feet for you to increase every time you go down. Which makes sense, because in a barometer, to get an atmosphere of pressure, the height of a column of water is what? It's 30 feet, right? 10 meters is about 30 feet. So, all right. We did this problem. What happens if I throw the block overboard to the level of the water? Let's just step through this so that you're sort of clear. It helps you to think about Archimedes' principle. You might have a similar problem or even a little bit different. But here, if I have, say I have a container, lake is sort of confusing, but if I just think of a boat like in a container like this, there's an object in it, and here's my water level right here. And then if I throw the object overboard, like a piece of steel or whatever, if I throw it overboard, the overall level of the lake is going to go down, and in fact, the boat will go up. You can sort of think of it in a couple of ways. You know, the boat is just displacing a lot less volume here because it's just not riding as low in the water. And so that's one reason that the water level goes down. I mean, that is the reason. But here on the left, the block is displacing its weight in water. And on the right, the block is displacing its volume in water. Let me write that down. And here it's displacing its volume. And the weight of water that's equal to that block feels a bigger volume than the volume of the block because water is less dense than steel. Okay? There's a very similar question, the beaker question that we did. We did this in class, in all the classes, I think. Where if I have two beakers and they're filled to the brim with water, but one of the beakers has a floating block in it, then which one of those has a heavier weight? The one on the left or the one on the right? Y'all know the answer? They're the same, right? So, and the key here is that the buoyant force is equal to the weight. The buoyant force is equal to the weight. When floating, the buoyant force is always equal to the weight of the object. Can I repeat that? When an object is floating, the buoyant force is always equal to its weight. If it's on the bottom of the thing, like right here, the buoyant force is small and the weight is big. That's why it's on the bottom of the lake or the container or whatever. But when it's floating, the buoyant force is always equal to the weight. And so this object right here, it displaces a volume of water, a weight of water that's equal to its weight, because that's what Archimedes' principle says, that the weight of the displaced fluid is equal to the buoyant force. So it displaced its weight in fluid in order to get a buoyant force that was equal to its weight. Okay. Number 12. We haven't seen this question, but it's still a good question. What happens to your buoyant force as you go to deeper depths? Does it stay the same? Does it depend on the volume of your body? Does it increase or decrease? Well, the key here is that the density of water is 1,000 kilograms per cubic meter. If the density remains constant, then the buoyant force is equal to rho Vg will also remain constant. Yeah. Are you thinking that the pressure increases as you go down? Yeah, that is true, that the pressure increases, but the density of water, because it's incompressible, stays the same. All right? Sometimes students get tripped up with that, but it's true nonetheless that this density of an incompressible fluid stays the same. That might not be exactly true. Like if you go to really deep depths, the pressure of the water can increase, like the density of the water might increase some, but when you're just talking about, you know, normal depths, it's going to be true that the density stays the same. And so if that density stays the same, then the buoyant force will also stay the same. Well, that's it on that test. All right. I don't know, other particular things? Yeah, Megan?
The apparent weight.
Yeah, apparent weight. You want me to just sort of address it again?
Is there like one way to solve for the apparent weight instead of it like given?
No, you mean in the old exams?
I guess in general.
No, there aren't really any apparent weight questions in the old exams, but you will see it tomorrow. So let's say that I have a block. And I tell you its mass is, I don't know, 25 kilograms, right? I know that that's the block that has that mass within it. But then, like we did in lab, where if I put it inside of a container that has some fluid in it, and then I measure its weight, like we did in lab where you have a string and you measure the force, weight of this object. And let's say that I measure the weight of this thing to be, I don't know, 1,500 newtons. So really I know that its weight is 2,500 newtons, right? But I measure its weight to be 1,500 newtons. That means that I have a buoyant force acting on this block that is 2,500, that's its actual weight, minus 1,500, or 1,000 newtons. Because it appears to be 1,000 newtons lighter than it was originally, than its actual weight. So, I mean, that's apparent weight, right? That something appears to be lighter than it actually is. And it appears to be lighter than it is because of the buoyant force. That the apparent weight is equal to the actual weight minus the buoyant force. And so the buoyant force is equal to the actual weight minus the apparent weight. I don't think about it in terms of equations. Just think about it in terms of, oh, this thing feels lighter than it actually is. That's because of the buoyant force. Right. Mm-hmm. Right, because the apparent weight, it appears to be less heavy to you because of the buoyant force. Okay? And then, once you know the buoyant force, you know, your buoyant force is equal to rho vg. So there are any number of things. You could figure out what is its volume. You can figure out the density of the liquid. That's really all you can figure out. The volume or the density of the liquid. Okay? It's not a difficult question. It's just you haven't really seen apparent weight that much except for in lab. But, I don't know, you know, tests are a good place to try things. You don't agree, do you? It's still testing buoyant forces, but I want you to not be thrown off by the apparent weight. That's why I'm telling you about it now. Okay? Any other particular questions? All right. Well, I think we'll stop there then. That's okay.